Okie doke. So last time we left off with a bucket loader with an excavator. So talked about different joints. Some links on that. Kind of got through that at Grosler's equation. Figured out how many degrees of freedom it has. Talked about different kinds of joints. So we'll talk about the idea of if you have like a hydraulic cylinder, how it's really two links on a sliding joint. So let's talk about how they handle that. We've already talked about rotary joints like pins and stuff like that. So let's call it that seemed pretty straightforward, and it should. So today I'm just going to hit one more and go from there, and it's to this guy. So it's a pair of vice grips, right? And it's more or less a pair of pliers, but not, right? One because of the incredible like gripping force, but can we describe in terms of mechanisms and linkages how this is different from the ordinary pair of pliers? How is that the case?
You don't need to apply the constant force to the handles for it to have a constant force.
Right, so, which is like a huge deal. So this is this mechanism has some stable configuration that holds the jaws closed. You don't need to apply any force for that to stay in that configuration. It's stable in that particular spot, which is like the big selling point of it. The other thing that's kind of a big deal is how the thing's made, because that enables that kind of which you can call it a bistable configuration, because there's more than one configuration that it is stable in, more than one configuration that it will just hold itself in. And and there's also the question of why the heck you can get so much more force out of these, and part of that's because of how the thing's made. So regular pair of pliers, so something like that. That's just a 2-bar linkage, right? You have a pivot in the center. That's it. 2-bar linkage. How many links and joints does a pair of vice grips have? Okay, tell them to me. So this guy here, I'm going to change it a little bit. So this guy here. Say again. Let's see. Have this guy here. Top jaw never moves. The top jaw appears to be fixed. If I try to move it, it ain't going nowhere. So this top jaw is part of this longer link. Okay. Oh, and before we leave that top one, how many joints does that top one have? Which is where?
Where it attaches to the bottom jaw and where it attaches to
this point over here?
No, it has to have another spring up to that.
Well, what's it called? The spring's just there for more or less convenience. So we're going to ignore the spring there. The spring might provide motive force for different things, but it doesn't change points of rotation. So we're just going to, we're ignoring it. Note that. It's there for convenience. If I cut it out, they'd still work. So we got those two pivots there, and the rest of that's all part of the same link. Okay, so that's one. Number two. Okay, so bottom guy links to that guy there. Any other pivots?
Yeah, to the bottom handle.
Yeah. So we got a pivot there. Okay, what else? Okay, so attaches there. Obviously. Great. Where else?
The link in the middle.
Great. And where else?
The link you use to open them.
Okay. So so this guy here, I'm going to ignore that one for the same reason why we're ignoring the spring. The spring is there for convenience. Ultimately, this guy's there for convenience too. If I'm moving it, it's its own little member in there. It doesn't affect the rotation of anything else in this. So we're going to ignore that call it escape link, if you will. You could get them apart without that. It would just be a lot harder. All right. So that's three. What else we got?
Link in the middle.
Guy here. Cool. Now, this middle link, is it actually attached to a pivot here? If I look into this guy, is that middle link actually attached to a pivot? Right, it's right. It just slides. There's actually no fixed joint there. It just slides on that ground, on that ground link. I'm just going to try to reshape this a little bit.
I feel like I could just call it out.
Yeah.
I'm not gonna do that because I'm gonna break it.
Yeah, you would call it, if that spring wasn't there, you totally could. Yeah. Which is again one of the things that the spring's there for. But again, it's just there for convenience. Doesn't change how the thing operates. That said, so this thing slides. What limits how far it slides?
The screw.
Right. So the screw is actually a link here, because unlike the spring, unlike the escape link, it actually does change how the mechanism operates. So you have that screw guy sitting in there too. That is also a link. So rather, you might say it defines travel. That's what links do. All right, so it's called, but that also kind of gives us one more type of link. we said that hydraulic cylinders, it's a sliding link as opposed to a rotational link. The screw is a helical link. It's another way to allow motion. So screws we can count as a kind of joint, if you will. That's probably a better way to say it. It's called it is what makes this interface. I guess is that let me to revise this statement because it's a joint, not a link. Sorry. Yeah, go away. There you go. It is a joint because it makes that intersection between the sliding part and the upper part a true joint instead of just two independent sliding members. So, how many links? How many joints do we got? Sorry, it makes. Dang it! I'm pushing myself again. Sorry, I'm confusing myself. I'm confusing myself. It makes this a joint, and this in and of itself is a link. There are 4 joints. Yep, and 5 links. Okay, so based on Grobler's equation, how many degrees of freedom do we got? How many do you got? 4. So 5 minus 1 is 4 times 3 is 12 minus 2 times. Yeah, you're right. It should be a double in here. Hang on. Oh, because we have two. We have 2 things meeting at this joint. So you have to double count that joint. Yes. Yeah. Why does 2 degrees of freedom make sense? I mean, I just have to do one action in order to use them, right?
Yeah. But so does the one action to open and close?
Yep. Yeah. If I could keep asking me that. So the one action is if I move this bottom link, I open and close the pliers. I only have to apply input to one link in order to operate these. So therefore, I always have a ground link. That's why you don't care about the fact that I'm holding on top. So so that's like the definition of 1 degree of freedom, right?
Right.
So why the heck is Grobler saying 2?
Because of the script.
Right. Because this screw defines the action as much as my actuation of the lower jaw. Where I have that screw position is critical to the operation of device grips. Hence, this is a 2 degree of freedom system. Conveniently, one of them I don't have to move while I move, while I adjust the other. So it still makes it it's very, very simple to operate, but it is a 2 degree of freedom system. Um, so, so I say all this to say that it's not necessarily a bad thing to have 2 degrees of freedom. I wanted to just give an example of that because we've kind of been poo-pooing them when we talked about like the excavator and stuff. Like we wanted everything to have 1 degree of freedom because it's easier to manipulate. But we can design a 2 degree of freedom system or a multi-degree of freedom system such that it's still straightforward to operate. If we only have to actuate 1 degree of freedom at a time. Cool beans. Any question with the vice scripts? Okay. Before we move on, oops, just scroll. There we go. So we've talked about, oh, come on, do what I want to do. We've talked about multi-degree of freedom structures. So there's my little 4-bar linkage, right? We said that, which we can figure out that. That's kind of ones that we're interested in because they move. We started off by talking about 0 degree of freedom structures. So like a triangular member. We said that those can be nice if you want like a structural thing. So we can think about Gödel's equation as not only being convenient for moving mechanisms, but also for if we design a structure saying, will this be statically sound? Another way we can think about it. We can also look at this from another point of view. How many degrees of freedom does that have? Say again? No, it does not. How many links? How many joints? 1 link? Are you including the ground? Okay, so 2 links, 2 joints. How many degrees of freedom? Yes. So we have a 0 degree of freedom structure. We have greater than 1 degree of freedom structure. We have a negative degree of freedom structure. So it's not just unable to move, it's actually stressed in place. So this is an example of a preloaded structure. So this be, as you can see, like an arch. An arch isn't stable until it's loaded, and then its weight keeps it in place. If it was a if it was a 0 degree of freedom structure, it wouldn't matter. I could bolt the thing together, throw it into space, and it would still stay in the same configuration. If I have this preloaded structure with this negative degree of freedom, I throw an arch in I throw a stone archway into space, it just kind of dissolves. That load is an important thing. So this is kind of an interesting aside. But let's get into more interesting things. So, question that we're going to be looking at is: can we determine something about the motion of a single degree of freedom structure? Answer is yes, but it gets interesting. Why? Going to pop over. I'm not going into add yet. Pop over to a website. Okay, this is the one that's on your homework there. Get the animation started and start tracing the different things. Okay, there we go. So if so right now link A on the left is the crank, and then you have the rocker, it's B, and then the coupler, they're just tracing out the midpoint on that. So what happens as I start changing some ways? If I make everything exactly the same, say it's the same length, it's actually kind of cool. You can get a 4-bar linkage that keeps the coupler entirely level throughout its entire range of motion. That's kind of neat. What we're going to look at first, though, is I'm going to make one of these lengths very short relative to the other. I'm going to cut this guy down by a whole heck of a lot. So it's still making a full circle. I have to make that really big. But C is scribing out a very small line. It goes from a relatively curvy line, if it's closer to the same length as D. The closer in length I make it to D, the more of a circle it traces out at C here. But the longer that I make it relative to that input length, the more of a straight line it starts to trace. So you might think if I could make an infinitely long output length, it would actually trace a straight line, right? And that's so let's look at that. We're going to say, what if I have some crank here, and it's connected by a coupler to a slider, which in effect is a rocker of infinite length. Okay, y'all follow that? Let's draw it. Let's draw it out. Maybe that'll make it a little bit more straightforward. All right, so here. All right. So there's my crank. It's just a wheel. I'm going to attach a link to it that attaches to a block that slides in a channel here. There's also a pivot on that block. Just an aside, it is recommended for sliders that they have a length greater than 3 times their diameter to help prevent binding. The controllers comes from St. Venant's principle. Diameter or equivalent diameter of the slider itself. Diameter width
Oh, the slider like
Yeah,
piece is like a little piston.
yeah.
Okay.
Or it could be a square block.
I was imagining a square block.
Yeah, it could be that. Yeah, it could be that. It could be that too. So, question is, how many links do we have here? Before we get too far, let's try to get an idea of the motion. How many links do we got? Keep going. What do you do? Let's start there.
The wheel is like an equivalent, and then wind point is an equivalent.
Yep.
Bar. And then the one run from
The
outer ring.
coupler. Great. So this is your crank. The thing that rotates. It's your input. This is your coupler. What do we say about sliding joints? The slider itself is the joint, and the track is because we're treating that as the ground. We're measuring out everything relative to that, right? So, or at least we could if we wanted to. You always need a ground length, right? We need someone to measure things relative to. We also call this the rocker. And if we were thinking of this as being on the end of an infinitely long arm, you could throw your ground there if you really wanted, if you really wanted to. But regardless of if you think about it in that sort of a framework, the fourth link is our ground link. So this is a 4-bar linkage. Ostensibly. How many joints do we got? 4. Which 4?
The middle of the circle.
Okay, that's joint 1.
Where it's next to the
Yep. Yep. Right. So the channel that it's sliding in. 4. So for links, for joints, how many degrees of freedom? Yep. So which makes sense. This is actually it is fundamentally exactly the same as our little 4-bar linkage. Just one of these links has an infinite length relative to the other. It's very long relative to the other. So that says to us one input defines this. And conveniently we have that. We have this wheel, we turn that wheel, that defines everything about the motion of the system. If I know the lengths of everything there, and I know the speed that's rotating that, I should be able to tell you how fast everything's moving, where everything is, all that sort of thing. The 1 degree of freedom system. So as such, let's do some math and see if we can figure that out. So yeah, erase a bunch of the intervening stuff. That is exactly what it is. Yeah. It should call whole for an engine piston. The only difference is that the motion would come from here instead of from the crankshaft. But yeah, that is exactly what it is. let's find some stuff. So we got some radius there. We'll say that this we call it's moved to some angle for theta. Say this bar has some length L. Don't know anything else? Not really. We'll assume that the center of the wheel and the center of the slider lie on the same line. That makes our life a little bit easier. And let's go to town. So so we want to relate the motion of these different things to each other. So if I set up an origin right here at the center of the wheel, I'd like to know how far away the slider is from the center of that wheel at any position of the wheel theta. Eventually, I'd like to find velocity too, but if I know position, I can get velocity. Just take a derivative. So, see what we got. So if I'm some angle theta, how can I express the location of this slider relative to the center of the wheel using what dimensions I have? Might make it a little bit easier. Actually, try this a little bit. Okay, so I want to find XS, and this is all the information that I got. How do I do it? What? Trig, yeah.
Just gotta wrap my head around.
Right. So R over here. So I know that that little bit there, that's that's a little bit of horizontal distance. That's a little triangle there, formed by the radius. Then I got this second triangle here, formed by the length. So the first bit, this distance here, that's pretty straightforward, right? That's if I wanted to find this first distance here, how to get that. I'll erase my angle thing. There it is. Yeah, that's straightforward enough. Call it theta crank. All right, so I got that first bit. Now I have to find the second length, kind of the bottom of that triangle there. This one gets a little bit more interesting, right? So if this link here was perfectly horizontal, call XS would just be R plus L, right? That'd be it. That'd be how far away the slider was from the center if this coupler was perfectly horizontal. But it's not. So how do we deal with this? We know that we need to do like L times the cosine of some angle here. The question is like, what the heck angle is that, right? We need to use an angle. Now we're talking.
Well, we don't need to find the angle of that one, of that triangle, because we know, at least in my mind, it's easier to use the theta, because just give it to
Right.
use that to find the vertical
Okay.
And then integrating these Pythagorean.
Okay. Yeah, totally. We can do that. And you can also use that to define an angle and
Yeah.
go backwards if you want to use more tricks. So yeah, you're right. We can find the height of that triangle. And it's, to think of it's less of what we're given than this is all the information that we can reasonably expect to have. We can find h, that height, r sine crank. I either want to find that angle there, or I want to use Pythagorean theorem to get this, call it x link, or xl. So I could say xl squared plus h squared equals l squared. Therefore, xl equals squared minus h squared. That is an entirely valid thing. So I could do something like that, an entirely valid thing. And I kind of like that because it puts everything in terms of theta crank, puts everything in terms of variables that I start with. So let's run with that. That gives me the position of the slider for any theta. Cool. So as you might imagine that in first there's going to be some sinusoidal motion, which makes sense, right? And I can adjust that. I can dial it by changing the value of L or the value of the radius. I can kind of dial where X is, how much was stroke that piston has. However, I'm also interested in how fast it's moving, right? That'd be a thing of interest. So I know that velocity is just the time derivative. I'm just going to take the derivative of all that with respect to time. So velocity of the slider. Radius is a constant, or is it going to change? Yeah, totally. If I'm taking a derivative with respect to time, that radius isn't going to change with respect to time, unless like the disk wears down and somehow gets smaller or something, which it's not. Or if there's like a black hole. L, is that going to be a constant? With respect to time? Yeah, it's not going to change. I'm going to treat it as a rigid member. So that means that derivative of cosine theta with respect to time, because theta will change in time, right? Because this is called, if I treat this thing as spinning, and either because it's driven or because this guy is driven, either way, theta is going to be changing with respect to time. So that means that theta is not constant. And we'll call the time derivative of theta omega, right? Or the angular velocity of the crank. And then derivative of cosine is what? Negative sine? Cool. So that's negative omega r sine theta crank plus, I have a square root thing here, so chain rule's fun, right? 1/2. L is a constant, goes to 0. R is a constant. Don't have to worry about that. I do have this sine squared theta crank thing. So if I do derivative of that, like what? 2 This is the inside. That's what? Like that? Is that true? Make that an omega. That's the first one. So we did that out with the chain, with the old chain rule. All right. That means 2 cancels out with the 1/2. I like a omega sine theta cosine theta times L squared minus R squared sine squared. Negative 1/2. Cool. Yeah. Yay, trig. So what this implies, though, is that say that we're driving the crank. Say that we're inputting an angular velocity. So that's constant. Yeah. I'm just putting in an angular velocity. Will we have a constant velocity on the piston? No, and that makes sense too, right? Because the piston should travel out and back, out and back, out and back. So we should anticipate its velocity also being sinusoidal, which we get from all these trig functions. You can still dial it the same way that we could before using the radius and the length of that length. The radius looks like it's the dominant one here because it's directly related instead of being related by a square root, which makes any difference smaller. But we can still dial the velocity of the slider relative to the angular velocity of the crank, just by changing the radius of the crank or the length of that length, which is intuitive. So this is a relatively simple example, but it also kind of provides us with the framework of if we wanted to find forces here, we could. This force is mass times acceleration. Well, this guy has to be experiencing some non-zero acceleration since the velocity is changing. So if I took one more derivative here, I'd get the acceleration of the slider, throw that straight into F equals ma, as long as I have its mass. And I can get the force acting on this coupler. And from there, I could find stresses and all that, and all that sort of torques necessary. Blah, 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 blah. So you can kind of see how this can connect everything else that we've been doing this semester. Once you can define in motion, if you can define positions, you can find speed just by taking a derivative. Once you find speed by taking a derivative, you can find acceleration by taking a derivative. Once you find accelerations, you can get forces. Bam. That is that. So, but don't worry. That's not really going to be the focus of what we're talking about. We're going to talk more so about designing these things first. So, any questions on this part? Cool. All right. So so we talked about trying to understand how mechanisms move. Let's see if we can put together a mechanism to kind of apply that understanding. So given how much time we have left, I don't think we'll get beyond the problem statement, but let's try to get that. So I'll start with something simplistic. We got a truck. Yay, we got a truck. It's just going to be a big bin. So has a big bed in the back. We want to dump stuff in the bed. Rather, we want to scoop stuff off the street and dump it into the bed. All right, so we have to have some kind of scoopy thing that's attached to the truck somehow. and eventually it lifts over the top and dumps things in. Sort of like a sort of like a garbage truck, but different. So there are a bunch of ways to do this, right? I mean, a garbage truck obviously has one way of doing it. It actually uses an articulated arm, where you can change the position of this part of the scoop, as well as adjust the position of the other end of the scoop. That's one way of doing it. We're going to look at doing it just by a 4-bar linkage for an example. Although you can apply this to the same technique to any sort of set of linkages. This is called the method of precision points. So the idea behind the method of precision points is that it starts off as a very graphical method. The idea is that you say, okay, I need to do this. I have a thing that'll kind of that'll affect what I need done. In this case, I need to collect, say, balls off of the ground, and then I need to dump them. So I have something, it has an open top, closed bottom. It'll let me do that thing. In other words, I have an output link. I design a link that affects the end that I want. Now I have to connect that somehow and actuate it. I also have to get it to do this particular motion. I have to get it into this configuration from this configuration. So defining those configurations and exactly where they are in space, that's the precision points part of this. So I'm defining one precision point here. Presumably I have dimensions for this truck, at least conceptually, and I know exactly where this thing is in space. I also know where this position is in space. I know that it has to sit on the ground. I might not know how far in front of the truck it necessarily needs to be, but I can at least set it out there for right now. Just try to keep in mind, I probably want it as close to the vehicle as I can. That requirement's a little. That requirement has a little bit of flex in it. I also want to define, just for kicks, I just want to pick a spot between those two. I don't necessarily care as much about this one. Just define another intermediate position. And that intermediate position is going to help me to check whether or not I have a valid solution. You might have more than 2 precision points. In this case, I have exactly 2 points that I know this thing must go to. In other words, down here at the base and up here at the dumping unit position. The link must go to those 2 points. And then it has to travel to somewhere else in the middle. The next step, which we'll do on Friday in CAD, is kind of picking a couple arbitrary pivots. In this case, we're going to use a 4-bar linkage, just for example, and connect where that pivot would be on the output link in each of those positions. And what we're looking for, make this one in red, is when are there any things that blatantly won't work? Like for example, I have links crossing here. That ain't going to work. Or at least it has a high potentially will not work. Which calls, so in order to change that, I might have to move a pivot around. And then we can also use this to look for things like dead links and so on and so forth. But we'll get more into that on Friday. And we'll try to draw this up in CAD because it's quite helpful for identifying stuff like that. Any questions? Cool. All right. Well, that's all we got for today. Thanks for stopping by.